Okay. Is anybody absent Thursday for the test? Okay. So here's the plan for the day. We'll finish going over the notes for set 10. And you should be able to do the homework then. I understand that review 9 at said the key was going to be on my website and it wasn't. I'm having a little trouble with the scanner, but I dug up an old one, so that'll be fixed. And the keys to 8, 9, and 10 will be there tonight. Now, it's important that you try and look at those as much as possible because we're getting a little more behind than I'd like. So try and minimize how many questions you have coming in. If my work's either wrong or just not clear, then I'll be happy to help you tomorrow. But again, try and get all questions answered to the best of your ability. The reason I don't know how much homework we're going to get to is after I do the lesson, finish the lesson, I'm going to hand back the test and you're going to start to make corrections on it for some points back. I'll explain that later. That took about the whole period. So, yet again, I did not have anybody turning in homework. So, that said, let's move on. Do you remember from the other day we talked about infinite rectangles, or at least we started with finite rectangles. You remember that? Okay, I don't remember where we left off, but let's catch you back up to speed. Remember, you can estimate the area under some curve f of x over an interval from a to b by summing many rectangles. Yes? All right, now, delta x, oops, that's delta x. Delta x represents what? Ah, I taught you well. Delta x is change in x. That is the base of the rectangles. And it's true, it is the change in x. You got me there. Okay? How do you find the base of each rectangle? What would into finding delta x?
B minus a.
B minus a, which represents what? The total region, and then we divide it into some number of chunks. So delta x is the base of each equal subdivision b minus a over n. The f at different x's represents the height of each rectangle. And it actually comes from two places. The x at which you draw the height depends, first of all, where you start. If I want to know what is this x, or this first x, it's from where I started plus how much I went over. So that makes x your starting point A plus some number of delta x's. The first height would be 1 delta x over. The second height would be 2 delta x's over from the starting points and so on. Does that sound familiar? Okay. Well then, let's get caught up as far as where do we leave off? Where are we? There. We did not. Oh, we did almost get through there. Okay. So by way of getting caught up, let's do this one together. Say I wanted an equation for the area of that based on any number of right-hand rectangles. I typically start basic, which is to say the basic idea of delta x is the base and f at x's is the height. Then I gradually work towards more problem specific. In this case, delta is what? 3 over n. I'm going to divide the region that's 3 wide into n chunks, and each equal chunk would be 3 over n wide. F, as I said, the x at which you're finding the height depends on where you started, which in this case is 0. That's wonderful. Plus how many deltas you've gone over, which in this case would be 3 over n each time, and 1 time, 2 times, 3 times, 5 times. You follow? Okay. From the first rectangle through the last rectangle, the summation goes from I equal 1 to I equal n. All right, a little more specific. 3 over n is fine. Now we can actually plug in the function. If the function in this case is 1 plus x squared, then this would be 1 plus 3 over n I all squared. Or 3i, I guess I could have put that 3i over n. Would have been a little more friendly. We? All right. Then we started doing a little more cleanup. 3 over n times 1 plus 9i squared over n squared. The whole goal then was to start to get rid of the summation notation. So we have these rules for, hey, if you have a constant added to itself so many times, you could use this formula to find what c plus c plus c n times would be. If you had 1 plus 2 plus 3 all the way through some ending number, then you could use that formula. If you had 1 squared plus 2 squared plus 3 squared through n squared, you could use that formula and so on. In order to use those formulas, though, they need to be cleaned up. So this, for example, when I distribute that, I could pull the 3n out front and just focus on what would 1 plus 1 plus 1 plus 1 plus 1 so many times come to. And I could furthermore take the 27 over n cubed out front and just focus on what would I squared, or 1 squared plus 2 squared plus 3 squared and so on come out to. So far so good? Stop me if you have a question. Well, once you get to that step, then you have formulas you can put in their place. 3 over n is times, how would you add 1 plus 1 plus 1 plus 1 n times? What would that come to? 1 n times is just n times 1, or n. 1 squared plus 2 squared and so on. That's a formula for sum of squares. I will give you these. You do not have to memorize these. So that is n times n plus 1 times 2n plus 1 all over 6. We? Okay. So the idea being that you just found a formula for the area based on any number of rectangles. So if I said, hey, this curve, estimate the area of that curve using 5 rectangles, then you could just plug in an n of 5 in here, and boom, you're on your way. You could plug in 7 rectangles, and that would give you a different estimate. You get perfect area by infinite rectangles. To take n to infinity, you probably need a limit, which we'll come to in a second. But before we get to that, let's try a few where you don't start at 0. You can see these feel kind of the same. The difference is here. You're not starting at 0, and that makes things a little ugly. It makes for a tedium, basically. So let's do one together where we're not starting at 0, then you'll try one. If I took the area of a bunch of rectangles, then I would first need to find delta x. What's delta x for this problem? 2 over 8. Okay. Remember the x at which you find a height comes from where you started and how many deltas you went over. So where did you start? 2. And then how many deltas would be 2 over n some number of times. Now that, once you've done a couple of these, you start to see that it makes life so much harder, because now you're going to have to do a little binomial expansion. Instead of just x cubed or that cubed, it's the binomial 2 plus 2i over n cubed. Binomial expansion. Do you remember the binomial expansion for a cube? A plus b, quantity cubed. A
plus b minus b. What are you looking for?
Okay, so let's first make sure you're not giving me this. I am not asking for the factorization of sum of cubes. That's different. I'm asking for the expansion of a plus b all cubed. So that is a cubed plus 3a squared b plus 3a
Squared.
plus, and those coefficients you can either find by Pascal's triangle or combinations. Why that is, I don't have time to teach that, but I'm sure you knew it at one point. All right, so if I apply that here, then I have 2 over n times the cube expansion of that a and that b. What's a cubed? 8. 3. What's a squared? 4. What's b? 2i over n, right? 3ab, I'm there. I did that, now I'm here. 3ab squared, there's 3. What's a? 2. And what's b squared? 4i squared over n squared. Plus b, got that one done. Now b cubed is? All that. All right. Here's then where we start to break it into little pieces. I'm going to do 2 things. I'm going to distribute and pull the n-ish stuff out front. So for example, here, I could actually go 2 over n out front and leave 8 in the summation, or I could just pull the whole thing out, 16 over n out front, and leave 1 in. It's the same either way, it's up to you. I just like to pull 16 over n out and call it 1 if I take that whole thing out. You see where I'm coming from there? Okay. If I then distribute here and pull out the non-I-ish stuff, what's 2 times 3 times 4 times 2? 48. How many n's in the denominator? 2, n squared, and what's left in the summation? Just a single I, yes? Okay. When I distribute to the third term, what's 2 times 3 times 2 times 4? That's the same, right? 48. And to the what now? Cubed. And the summation is of I squared. And the last distributing is 2 times 8. 16 over n how many? 4. Sorry, my handwriting is bad. That's a cube. And I cubed inside. Yes? Last but not least, we replace with formulas. 16 over n. What's the formula for adding 1 to itself in times? 1 n times is n times 1. Are you clear where that's coming from? Right. Rather than just writing, you understand it? Okay. All right. What about this then? 48 over n squared. The sum of linear factors is arithmetic, so that's n times n plus 1 over 2. This is much harder to come up with. And this, the cube is my favorite. The sum of cubes is actually just like the sum of linear factors, but squared. Isn't that crazy? Sum of 1 squared plus 2 squared, all that squared would be, that's some cube. It's crazy. For each term cube. All right, that's all you had to do. We're going to take the limit in a second, but for now, that was all there. Try this guy. Oops. Try this guy on your own. If you consolidate a few steps, that's up to you. You're going to have to know yourself and what you can keep straight in your head. Okay. I'm going to give back some papers while you're knocking that one out. this week, but you may get a homework check type quiz or two. Is that right? Let me catch up to you so you can check your. So, how did you do that? Do you feel like you have that? Or a question or error if I didn't? Well, give me some feedback, okay?
No.
Okay. Yes? How do I know which of these to use?
Yeah.
Yeah. It really has to be the case. In your shoes, I probably wouldn't know until I finally get the I isolated or the I squared isolated. But you have to isolate the I term to make the call. Once that's done, then once I see, oh, that's the sum of i's, that's what tells me to use this formula. You see what I mean? And once I get I squared, so if you're looking at the big mess, you probably don't know. It's just when you isolate. Does that make sense? Yes?
And you said we get these on a test or whatever?
Yes, absolutely. I'm not big on memorization in terms of college. The questions I've seen, they give it to you. Yes?
So,
Did you have a question?
yeah, I think, so is it just expansion? Did you just square, like how did you get the 4i over n in the middle?
Let's go
And did you
1, 2, 3, 4. How'd I get here?
so between 3 and 4, you just squared it? So
Yeah.
like you would normally would?
Yeah, so I thought a plus b squared is a squared plus 2ab plus b squared. So this comes from 2 times the 2 terms. So 2 times 1 times that. That's what that came. Okay, now let's put it all together. Taking now the number of rectangles to infinity. So we're going to do all that stuff we're going to find a formula for area of rectangles, but then we're going to take the number of rectangles to infinity. At the end of all that process, we're going to take the infinite limit. So this one's back to the nicer case. You can see we're starting at 0, so there won't be that binomial stuff here. It'll be a little nicer to start with. Let's go with a little more specific. Delta from 1 to n. What's delta x in this case? 2 over n. F at what x values? Remember, it's the start plus the change.
2 n times I.
2 over n I times. Yep, perfect. Please stop me if you either disagree or you're not sure where I'm getting. Then what do I do? Yeah, plug in the function. In this case, the function is 1 plus 3x squared. So 1 plus 2 over, we do this cleaner, bracket, 3 times blank squared, and in place of x squared, I'm putting 2i over n. And this kind of goes to how quickly you can do things. If you want to do a cleanup step and then distributing it and simplifying, fine. If you want to do it all in one, fine. I think if this were the whole thing squared, I'd probably take it in 2 steps. But because that's just that term squared, I think I can get that straight in my head. So 2 over n times 1, that would be a 2 over n out front and the summation of just a bunch of 1s. Follow? This would get squared, so it's 4i squared over n squared. Then times 3 and times 2. So 24 over n what?
Cubed.
Cubed, I agree. And the summation of I to the what? Squared. All right. That's pretty good. Then what? Substitute in the known formulas for those summations. 2 over n, what's the sum of 1 n times? N. And what's the sum of 24 over n cubed times the sum of squares? And times n plus 1 over 2n plus 1 all over 6. All right, here's where it's delightful to teach you guys in your knowledge of n behavior. The limit of that, you do not have to show a ton of work. Just use your n behavior knowledge. So when you simplify this, the n's drop away, and the limit of 2 is just 2. What about the second limit? It's not so easy. Imagine what it would be if you expanded it out. Look at just what the dominant or lead term would be. It would be n cubed. What would the coefficient of the n cubed be on the top? Are you going to cancel first? Or how do you want to do this? Okay, say you cancel. That would be 1 over 4, yeah? Then when you expand it, you'd have 4 times n times n times 2n, which is 8n cubed over what on the bottom? N cubed, giving you 8. And so your final answer is 10. Yes? All right. Try one of your own, please. Use the steps above. You take notes for a reason, obviously. Use the steps above if you need to, but try to come up with the steps on your own and look at your notes as little as possible. Excuse me. Add a couple of big homeworks to him. Maybe 2, I can't remember those. Okay.
Can you go over how to?
Yes, I will. I got 27 halves. How about you? Okay, what stuff?
When you're like distributing things that n goes to infinity, like for the n times n plus 1, I understand that you can cancel the n squared, but what happens to like the plus n? Like do you just disregard that instead?
It's because it's an infinite limit, it's just about the end behavior. So it's, although technically this is the limit as n goes to infinity of 9n plus 9 over 2n. As n gets infinitely large, when I put in a billion, adding 9's not going to do anything to that, so it becomes,
Oh, okay.
so it's in behaviors. Okay? Other questions? Did that go okay? Yeah. All right. Unfortunately, I didn't put one in the notes about starting at someplace other than 0 all the way through, but it's a lot like we did earlier, just with the limit attached to it. So on the homework, I think there's more than you should be okay. I think. All right. So let's talk test, shall we? It's the no. I can just say to get corrections and leave it. I definitely don't need any more grades. But in the interest of learning. All right, the first page is the happy page. You'll probably be okay or happy or overjoyed even with how you did on the first page. I'll talk about this in a second, and I'll hand out the second page. Oh, if you please, I am trying to keep data from year to year, same test, and so I cannot have the test released. I will take these back. So towards that end, what I'm getting at is, would you put your phone away? If it's out in any way, please put it away. If you do seem to have your phone out in an intentional way, I will consider it cheating, and you'll pay for it. Okay, so please don't have your phone out. So the test.
The justification.
No, I guess
It's okay, I'm sure you're gonna cut them out.
I got extra. Oh my God.
Okay. All right. A note or two about the first page, if you will. So, first, go to the front and unless you earned +2 on that number 2, then it was lacking. So I would like to talk about that. This is not correctable for points bad, but I do want you to learn because this didn't go well. I was put it on the calculator page. I shouldn't have, but I do want to assess it. So in other words, you're going to see this again. So I hope you learn. The idea on number 2 was to show analytically why there has to be a solution or an intersection between these two. That does not mean pick up your graphing calculator and estimate the point of intersection. First of all, can't be done. You cannot find that exactly. Sine of most things is irrational. It goes on forever. You cannot name that solution. Just can't be done. And so you're estimating it at best, and that's not what I intended either. So with that said, this is what I intended. You use the IVT. First and foremost, IVT works for one function only. If it's the case that they give you a combination function, it's on you to know, oh, wait a second, if I need to know where these are equal, and I need to make it one function, I should move everything to one side so that I can then call this one function. Let h of x be that. The equivalent question then is show there is an intersection would be to show that the combination of the two or the difference between the two is 0 somewhere. You with me? Now, show that curve, whatever it looks like, must pass through 0. Now it starts to feel like IVT. You could, some of the homework I made you figure out points on your own, -10 and 10. I'm giving you points here. I thought I was throwing you a bone here. I gave you points. It didn't go well. First of all, to IVT, you must state that h is continuous, is it? Is sine continuous? Yeah. Is linear continuous? Yeah. Does adding a constant change that? No. So h is continuous. Check. You don't really have to rigorously prove that. You just have to give it a thought. Now, at 0, what is h at 0? 1/2. Okay? Oops, sorry about that. I didn't want to get through that. What about h at pi? Over 2, sorry. 1 minus pi plus 1/2. What about 3/2 minus pi? I don't know what it is exactly, but I do know that it's negative. Is that enough to conclude that the combination must have been 0 or the difference between them must have been 0 at some point? Yes, and then you do your IVT stuff. h must equal 0 in between h at pi over 2 and h at 0, and so by IDT, blah, blah, blah. Most people are fine. All right. Are you with me? Okay, good. Number 1 you should not have missed. If you missed number 1, you should feel a little bit ashamed, okay? I don't want you to feel really bad about yourself, but you should feel a little ashamed. 3 was fine. 4, a lot of people went, which one was the common mistake? People said the last one is a derivative. Why isn't the last one a derivative? Oh, no, sorry, which one did they choose? Oh, no. Yeah, no. What's the mistake? What was the right answer? 2 only? On number 5, I'm sorry, I'm on number 5. Sorry, I'm on number 5. No wonder you're confused, I'm jumping all around. On number 5, which of those could be the derivative at 1? 1, yes or no? Why not?
How did we end it?
Yeah, it ended wrong, f of 1, right? F of x plus h minus f of x, and that was ending in f of h, so that's why 1 was wrong. Most people knew 2 was the alternate definition of fine, and then most people didn't have a 3. That's just the general definition, and not that 1. 6, not one person missed. Great job there. Go to the back, please. All right. Now, this used to be more valuable before Ms. Kennett started teaching here, where people made a lot of mistakes here, and corrections for points back was super necessary. You guys know so much from Ms. Cannon that the average on this was like 6 or 7. That's pretty doggone good, I gotta say. That said, I still want it to be a learning experience, so you may make corrections for half points back on the back. When you do corrections, I prefer you do it on this paper if you have room, but if you need to attach a sticky note or some extra paper, that's fine. Please do the corrections in ink if you do them on the paper, so I know what's original, what's new. And let's see, what else do I need to add? I guess it goes without saying, I'll have to say it. You have to tell this to the field. When you do corrections for points back, it goes without saying that the corrections must be correct. That's why they call them corrections, not incorrections. Okay? I'm not giving you a doggone thing back for doing it wrong again and wasting my time further. That makes me really frustrated. I will give you time to work on these together. A and B, very few people had problems with. Would you like a little point in the right direction with C and D, or no? Okay. All right, good. C and D, if people had errors, and I had several 9s, so not everybody had errors. If you are one of those 9 people, just chill, be proud, and help others in a second, but let me point them in the right direction. C, I know it's been a few days, almost a week, so let's look back at it. It says, find the coordinates of the 2 points where the line tangent to the curve is vertical. It was very common that people mistook or switched vertical and horizontal. Vertical. Vertical means this, yes? Wouldn't you agree that from this point to this point there is rise, but there is no run? So you need to set the denominator equal to 0. That gets you started. Then it says coordinates of points on the curve. Well, once you have that, will that be then an x or a y you're finding when you find the denominator equal to 0? Y, all right. Then you have to go back and find the x's that go with them. Where do you put that y when you put it in? Yeah, into the closed curve. One more thing while I'm thinking about it. I had a lot of people say, you can't do that because the function is this or blah, blah. This is not a function. It is not even close to a function. You'll see that there's curves that look like this, and when they say planar curve, that means it's in a plane as opposed to 3 dimensions, okay? It's not a function. Don't call it a function. They won't take off on that, but a professor most definitely would. It's not a function. All right. So, does that kind of get you going in the right direction on C? I'll assume by your silence that's a yes. It was this is actually a soft point. One was for establishing what makes the slope vertical, and then the other two were for finding the coordinates, knowing what to do with that, finding the coordinates. D, is it possible for the curve to have a horizontal tangent at points where it intersects the x-axis? This really has three conditions in it you have to meet. I think we talked about this on Friday, but to remind you, horizontal tangent. If it's a horizontal tangent, what does that imply? di dx is 0, which is to say the rise is 0 and there is run. So you need to set the numerator equal to 0 for a horizontal tangent. That's one condition. The numerator of the slope, the derivative, needs to be 0. What's the next condition? Intersects the x-axis. What does that imply? If it's at the x-axis, what do you know? Y is 0. Okay? Now, that's great, but it also has to be the case that these are actually points on the curve. Now, let me make this very clear. I'm doing this in this order, but people did it in a different order. Some people said, well, for the slope to be 0, x has to be this, but the y for that point is this. So there are a couple different ways to go at this. I don't want to imply that it's one way or the highway. There are like 4 or 5 different approaches I saw. They're all mathematically sound. That should be enough. If you need help, ask your peers, and then ask me. And if you're not sure what I counted off for, let me know. While you're working on that, I'm going to then hand back page 2. Page 2 was a little rougher.
Oh. Did you get B?
Yeah.
How did you do it? I rephrased this meeting.
Oh, what the heck? I just made it 0. What was I thinking? Why not 0 at least?
Oh, it's fixed. I found where there was a horizontal tangent.
Let's just lose half the point here because I said there's a vertical tangent.
So that can't be true because it doesn't go to 0.
Because now I see that thing.
It's I got off the 0. Then that.
Yeah.
Yes. So you
This is the point.
that started correctly with y equals 0. So that's where you yeah.
Only get points back for this.
Yeah, so actually it doesn't have 0 in the number. You could almost finish if you just say that this is not 0.
Right. Yeah.
Then you're home free.
I was thinking 0 plus 1 is 0.
That does happen. No, so you were this close to being perfect. No, that's good. It's great. Yeah.
I said 0 plus 1 is 0. I was an idiot. Number 1.
I don't know why I got it.
It's not clear what I want or what I need. Let me know.
Wait. As it goes to 1, that's 4. But then that's... Oh my god, it's terrible. Oh my god. Oh my god.
Come on.
Oh my god.
Yeah, I don't know what's going on.
I didn't realize it. Darn it.
Oh my goodness. I would prefer you finish the first page corrections. So I don't want to get too much into the second page, but just before you get too sweat the second page, you will be able to correct for points back on the second page, number 11 and the back.
Oh, thank God.
So we probably won't have time to do that. I will be collecting these in about 3 minutes. You may not take them with you. You'll finish corrections tomorrow. If you can knock out the first page's corrections right now, that would be great. If you need a little more time tomorrow, I'll be walking around, let me know if I can help.
Wait, are we allowed to do?
I'm collecting both things back.
Which ones are we allowed to use extra round?
Just
Oh, I read asymptosis. And darn it!
A lot of people did that.
Well, that's why I got confused. Like, how do you find tangents by proving it in limits?
That would be confusing, you're right.
So I basically just made it. And then I counted.
For 12?
Yeah.
Actually, I got what I did. I got lucky in bonus yes. Because I forgot the identity, so I'm just like,
Oh, it's.
I said 3.
Oh, but.
I got so lucky.
Yeah, well, let's. You don't have to take 3 sine of x over x. Yeah, you can split it up. Here, look at split it up. Oh, I distributed it. So you have sine of x, and then that equals 1, and then cosine at 0 is 0. Or is 1. Oh, I get it. You split it
up against everything.
You split it up 3 over 0.
Yeah.
Oh, yeah.
No, I was like, this doesn't
You got this. And you got that. No, cosine.
That wouldn't have worked either.
Okay, you just don't know how to split up.
I know.
Yeah. If you take it out
Yes.
once, why don't you just again?
That's true, right?
Oh, like because if you multiply by both together. Well, this would be
Zero would be
ridiculous.
0.
Well, geez, what you did would be 3 times sine x cosine x over x cubed.
For 11, did you get points? Or what did you?
Oh, for 11?
That's what I did. That's what I did, but he said equations. He said question mark. Oh, I think it's saying like what the answer to.
Oh, no, because it's a horizontal asymptote. Y equals.
Oh. And I said up to. I said limit as.
Okay,
Exactly.
when the bell rings, I turn this over and I got it.
Ninth graders, the bell down.
Oh, look at 1 out of 4.
I got 6 and an 8. Fire.
There too. You're gonna hand me both pages on the way out the door.
Dude, I can
Take
make
another
it.
minute or two.
So you're allowed to do 11 in the back. 11 in the back?
That is so, oh my gosh. It is a whole, oh my God. I got all the hard stuff. I guess you guys put it.
So you guys get C for 13 years.
I got 1 out of 4.
I got 2 out of 4. Because I didn't.
I did this one in 2 minutes, so.
There's a removable discontinuity at x equals 2.
Right, so when I got marked off on so if I just it is removable.
Okay, so
Oh, I
actually,
said it
I
was.
need both pages back. If you need more time on one page or both pages, I'll give them back to you tomorrow. But they must be posted in right now. I mean, not need them. Yeah, even if you need correction on the first page, that's fine. I'll get back to you. I got it. If you want to come in 7th, I can give you some back in 7th. I need them back. Just hand them to me on the way out.
Oh, yeah.
No, that's like trying to all That's so, oh. That was like the
I'll be amazed if I get
no, no, it's not.
I find the limit is 6 by 6 feet. Yeah, I kind of screwed it up there because I didn't know how to film before. It's not possible.
That's wonderful because I don't know how to do it. Oh, God. Yeah.
Oh, I have no idea what I was doing.
Have a good day. See ya. Thank you. June, it's so nice to see you.
Ooh, I feel good. Yeah. My sister wrote all the I.
Thank you. Have a good day. Thanks.
Oh, I did May and then later. Mr. Rickman. Oh, yeah, thank you. Okay, so just because these are two different functions, is that right? That it's really two.
Yes.
So each function has its own horizontal. Okay. Thank you. Okay, thank you.
Thank you.
I want to tell this photo. I have the
Oh, super. All right.
and it's
Earlier I came.
and then I can.
Would this be correct?
Yeah. Thank you. We see what you really. It's technically expensive. Maybe they're 24, so you really say.
Oh, right, not infinity.
Actually, so and it does go past you. Oh, you know. I just actually said that as well.
Oh, okay.
But,
Yeah, I see that. Cool, thanks.
thank you. All right, thanks, Kim. If I have backup questions, I will ask you.
Thank you.
Thank you.
Oh, God. I cannot get you. It's too difficult.
All right. Test
A
this.
bet to encourage or I do something bad. I'm just worried I'm not going to be able to.
Okay. Oh, shoot. Wow. Sorry.